Good morning, ladies and gentlemen, boys and girls, friends and neighbors. Today we're going to talk about partial fraction decomposition. This is strictly a BC topic. It is a BC topic that is certainly testable this year in one way or the other. Maybe there will be a partial fraction decomposition problem, maybe not. You usually use partial fraction decomposition integration when solving a logistic differential equation. Nobody's going to ask you to solve a logistic differential equation, but there may be some type of partial fraction integration that we need to know. The problem that I posted for April 24th does have a partial fraction decomposition differential equation on that, so we will solve that problem today, just to give you an example. So I'm going over this so that you can review this partial fraction decomposition integration. We did this a while ago, but it's certainly worth a review. So if I'm integrating this thing right here, I do not have a rule, and notice this is a quotient. I could multiply that out. This is going to be the same as this integral right here. 3 over x squared minus 3x minus 10. And even we should notice absolutely that there is no substitution is not going to work. Certainly by parts we use on products. This is a quotient. And if you have a quotient that you can write as a fraction, as we did here, usually a good strategy is to try partial fraction decomposition. What we have to do, why do we call it partial fraction decomposition? What we're going to do is we're going to decompose this fraction. And we're going to write it as a product of two fractions. So this we know. This is the common denominator, x minus 5, x plus 2 of this fraction right here. So what we're going to do is we're going to write it as a over x minus 5, where a is some number, plus b over x plus 2, where b is some number. And we're going to find a and b. And then we're going to rewrite our integral. So here, I'm just going to go through the steps. What you do is you're going to multiply both sides by, let me do a different color here. We're going to multiply both sides of this equation by x minus 5, x plus 2. Okay? And if I multiply this rascal here by this, what's going to happen? I don't know what happened here with these guys here. I don't know what happened with that, but oh well. So if I take this right here and multiply it by the left side of this equation, the x minus 5, x plus 2's will cancel, and what do I have left? I simply just have a 3 left. Then if I take this and multiply it by a over x minus 5, the x minus 5's will cancel, and what do I have? I have a times x plus 2. In like manner, if I multiply this guy right here times b over x plus 2, the x plus 2's will cancel, and I simply have b over x minus 5. And now what we want to do is figure out what a and b are. So how do you do that? The first thing you're going to do is, hey, you're going to let x equal negative 2. This method should become familiar with you. This is a pretty easy thing to do. It's a very simple analytical work. So if x is negative 2, wherever I see x, I'm going to put a negative 2. And what do I have? I have 3 is equal to a times, big giant 0, plus b times negative 7. And what does this statement right here say? Well, that says 3 is equal to b times negative 7. And what's b equal to? That says that b is equal to negative 3/7. Okay. In like manner here, ladies and gentlemen, I'm going to let x equal 5, because that's going to zero out this term right here. And what do you have? Let's see a different color. Let's just go green. So if x is equal to 5, wherever I see x, I'm going to put a 5. That says 3 is equal to a times 7 plus a big giant 0. And what does this equation here? This says that a is equal to 3/7. So now I'm going to take this. I know what a is, and I know what b is. Let me go down here. So therefore, this guy right here that is the same as this guy right here. A, which is 3/7 times, well, I'm going to have to go back up here to my original equation right here. Right here. This is what I'm going to use. A is 3/7 times 1 over x minus 5. So 3/7 times, pardon me, 1 over x minus 5. And then I have a minus 3/7 times 1 over x plus 2. And I'm integrating that. And that is true because we just found by partial fraction decomposition that this single quotient is equal to this fraction minus this fraction. Alrighty. So now, next step on this then is where this is going to be an easy thing to integrate. So we're going to integrate this right side over here. And what I'm going to do is I'm going to pull the 3/7 out, and I'm just going to integrate this piece right here. And what is the integral of 1 over x minus 5? That's going to be ln of x minus 5. Okay, and then I'm going to pull, now I'm going to integrate this piece right here. I'm going to pull the negative 3/7 out. And what is the antiderivative of 1 over x plus 2? It's ln of x plus 2. And then keep in mind we have k, the constant. If I want to clean this up a little bit, I certainly can. One way I can clean it up, at this point right here, you could be, this is not incorrect, but I'm going to do some algebra here. And I'm going to show you some nice algebra tricks here. What I'm going to do is I'm going to factor out a negative 3/7. I'm going to factor out just a factor out of 3/7. And this is going to be ln of x minus 5 plus ln of x plus 2 plus k. And true or false, this, by properties of logarithms, I have like bases. I could actually write that this way right here. Wait a minute, this is going to be a, made a little sign error there. Factor out of 3/7, so that's going to be a minus. So this is going to be 3/7 over ln of x minus 5 divided by x plus 2. Absolute value of both of those, by the way. Plus 2. And why is that true? And that's that simple property. That's that age-old property of, and we just go ln of a minus ln of b. This is in your pre-calculus books, is equal to ln of a minus b. Okay, but I will tell you, ladies and gentlemen, if you were trying to find that integration, you could stop here, and this particular answer would be a Happy New Year to this anti-differentiation. So this is what that is equal to. And how did I get there? I had to do partial fraction decomposition to take this guy right here and make it into 2 fractions. That was the key here. And this is the strategy for doing that, converting that fraction to the addition or subtraction of 2 fractions. Okay, so let's go one more example here on this video of partial fraction decomposition, please. And here we go. Okay, this is a differential equation here, and I want to solve this differential equation. And when I solve the differential equation, that means to find the value of, what we're going to do is find the value of y, or the value of f of x, if we possibly can. So the first thing we do with any differential equation is we're going to separate the variables. And we notice here that this side over here has all y's. So we're going to put that on the bottom, on the left side, and that's going to be 1 over y squared minus 2y. I have the dy on top, is equal to, well, if I divide by that, I just have a 1 dx. Okay. So this right side is going to be easy. That is going to equal, if I anti-differentiate, now that's the next step. I have to anti-differentiate. this right side is going to be super easy. The antiderivative 1 with respect to x plus a constant there. This is the rascal that I have to deal with right here. And there is, on the assignment that I posted today, you're going to have to solve a differential equation that looks like this guy right here. Okay, what do I have to do here? Well, I'm going to factor that bottom. And true or false, that's going to be 1 over y times y minus 2. Okay, that's going to equal x plus k, but what I need to do is I need to just figure out what this guy is right here. In order to do that, and I notice I have a product on the denominator, what I need to do is change this. Now this is an algebra, becomes an algebra problem. That is going to equal to some number over y plus some number over y minus 2. And then we're going to use the same strategy that we did before. Okay. Okay, we're going to multiply both sides by y over y minus 2. Okay, what do I have if I take this, multiply it by that? This guy is just going to be a 1. A over y times this, the y's cancel, is going to be a times y minus 2, plus, if I multiply this by b over y minus 2, the y minus 2's cancel, and I have by. And I'm going to follow the same process, because I want to find out what a and b are. I'm going to let y equal 2, and if y equals 2, what do I have? I have 1 is equal to this big giant 0 here, plus b times 2. What does that tell me? That tells me that b is equal to 1/2. Okay. And okay, so now I'm going to let I'm going to let y equal 0 here. Let y equal 0. And what does that tell me? That tells me that 1 is equal to a times negative 2 plus a big giant 0. And that tells me that a is equal to negative 1/2. So if I go back to my original integration problem, which was this, 1 over y times y minus 2, and I'll come back to the differential equation in a moment, this is going to equal this. Keep in mind, it's going to be a, which is negative 1/2 times 1 over y, plus 1/2 times 1 over y minus 2. And keep in mind it's dy. And why is that true? It's true because of what we did here with the partial fraction decomposition. I found the a, I had this fraction here, I had this fraction, and I decomposed that fraction, a over y plus b over y minus 2. And what I wanted to do was integrate that fraction. And this is what I'm doing right now on the bottom of the screen. Let's do that in black. I'm integrating that. I wrote it as this. Now I'm going to integrate the pieces here. And if I integrate this, this is going to be negative 1/2 ln of absolute value of y plus 1/2 ln of absolute value of y minus 2. Okay, and now let us not forget what that equals. This is equal to this rascal here. If I go back to the top, plus 1/2 ln of y minus 2, and that is equal to x plus k, because that was the antiderivative of the right side. So this is the antiderivative of the left side. And this was the antiderivative of the right. Okay, and if I come back up here, this is what I wanted right here. This is what I had. This was the right side. Okay. And so now, I started with this initial condition f of 0 is equal to 4. So what I'm going to do, I have to be very, very careful here. This time I'm going to factor out a negative 1/2 of both of these dudes right here. I'm going to factor out a negative 1/2. And what do I have? That gives me the ln of y minus ln of y minus 2. Negative 1/2 times ln of y is negative 1/2 ln of y. Negative 1/2 times negative, going to be positive, is equal to x plus k. And the only reason I did that is so that I can employ this nice law of properties, this nice law of logarithm. Let's multiply by the negative 2 to both sides before we do anything else. It's going to be ln of absolute value of y minus ln of y minus 2. And that's equal to negative 2x plus another k. You can call that k, we'll just make it a different color. This is k times negative 2. And so what is the right side then? The right side, by the property of logarithms, is absolute value of y over absolute value of y minus 2 by the property of logarithms. And that's equal to negative 2x. And now I can actually put my plus k, oh my goodness, don't forget the k. Now I can use the fact that my initial condition up here was f of 0, what was f of 0 is equal to 4. So I'm going to use the initial condition that f of 0 is equal to 4. I'm going to put 0 in for x and 4 in for y. So what do I have? So this tells me that ln of 4 over 2, 4 in for y, I have 4 over 4 minus 2 is 2, is equal to 0, k. So what's k? K is equal to ln of 2. Now, we could go through the process of actually solving this for y, but we're going to leave our equation like this. We're going to say, hey, the ln, and I can write it this way, property of absolute value, is equal to negative 2x plus ln of 2. Okay? And we're not going to worry about doing the laws of exponents on both sides. So that's a review of what you'll need to finish this particular problem. And if I come up here, let's go back. This is a good review of partial fraction integration. Okay, we have this guy that we integrated. And then we had a problem exactly like what you will see on the assignment. Okay, so talk to you soon.